It's my pleasure to introduce our next speaker, Bo Du for Polymer. Here we go.
Is anyone jet lagged? Raise your hand. Long flight? Okay, hopefully I don't bore you with this talk. I thought a lot about setting a North Star for what we're working on at Polymer and seeing a lot of the trends in the space, generally speaking. I changed the title of the talk a little bit. It's now increased bandwidth, reduced latency. If some of you folks are on crypto Twitter, you probably recognize this. So a little bit about myself. I am the technical co-founder of Polymer Labs, where we're working on connecting Ethereum rollups together in real time. There's this notion going around that rollups are the new server. And if you think about this, there are a lot of similarities between the two technologies. This is the first time that you don't need to run a distributed set of nodes, inherit blockchain properties. Instead, you're offloading consensus to a layer one, and you can run a centralized sequencer, you can run a centralized node, and still be able to derive some of these blockchain properties. But how does the performance of a rollup compare to that of a regular web server? And we want to make this comparison because we want to make it competitive for developers to build things on chain and succeed in existing app categories where it's quite competitive. Cost and performance or essentially handicaps that developers have to take on to build on chain. Let's look at latency first. What does the latency look like when we send a packet between rollups versus the cloud? And the numbers here aren't great. If you want to send something across rollups safely, you end up waiting 12 to 16 minutes for Ethereum finality. Not very fast. If you want to send something between the servers in the cloud, let's say within a single availability zone or across AZs, you're dealing with 1 to 2 milliseconds. So it's 720,000 times slower. What about the costs associated with sending a packet? What do the costs look like? So if we look at sending a packet across rollups in production today, it takes about 25 cents in the existing point-to-point interop protocol. And in the cloud, this costs a fraction of a cent. This cost is 357 million times more expensive. Now, how do we bridge this gap? How do we close this gap in terms of latency, in terms of cost? Let's take a lesson from the Solana folks. And you can see in the tweets that they're campaigning for this very simple North Star. Ethereum has a very complicated roadmap. This is far simpler. Why don't we just increase bandwidth and reduce latency? If we increase bandwidth, we can reduce the costs. We increase supply, costs come down. And we need to reduce latency to make things competitive for app builders. Let's take a look at step one. The way we can increase bandwidth is by reducing interop capacity while simultaneously reducing interop overhead. Think of this capacity as a pipe. So the wider the pipe, the more water that can flow through this. But the more efficient the flow, if you compress the flow, the more flow will fit through this pipe and the more bandwidth you'll have. Let's define interop capacity first. We can define capacity as a sum of verification and data capacity. Verification capacity captures the overhead of verification and protocol logic, while data capacity captures the overhead of the data, packet, and proofs associated with whatever security model that you're using. Now, what is interop overhead? Interop overhead is the amount of capacity used to achieve a certain level of security and latency. The way Polymer works with EigenLayer to increase this is Polymer focuses on increasing verification capacity, while leveraging EigenLayer, we can use them to increase the data capacity. Polymer also reduces interop overhead. We migrate interop costs from more expensive and unoptimized block space, or directly on the L2s themselves, over to Polymer, which is also an L2, where block space is less expensive and more optimized for this particular workload. On the proving side, we can convert from individual message proofs to leveraging ZK, and rollups is more expensive, as you can just look at the margins. If we look at the margin of base, they operate on a 98.5% profit margin. So if you're paying for interop costs within this more expensive block space, they're upcharging you significantly. To summarize, Polymer increases interop bandwidth by making more efficient verification. We have no VM. All of our code is implemented in pure Go. Increase data capacity with EigenDA and decrease data costs. And shifting interop costs into our block space and away from the more expensive block space and the L2s. Let's look at step 2 next. How do we reduce latency? Why don't we use sequencer preconfs? At the L1 level, preconf is a proposer or builder preconf. And at the L2 level, a preconf is a sequencer attestation. And we can see that there's 3 ranges here. From L2 settlement, starting with block production, when the block is produced, where you have this local ordering and validity guarantee that's made by the sequencer, to global ordering that's established once data availability is published to the layer 1. This can be anywhere between the range of 2 minutes or more, depending on how often data is published. And then at the final step, the state of the rollup is verified via the rollup native bridge. Whether you're using a ZK proof or a fraud proof, this process takes anywhere between an hour all the way to 7 days. And in the middle, we have the Lagrange state committee product. The Lagrange state committee product will attest to rollup execution once data has been published, and Polymer leverages all 3 of these verification mechanisms internally, depending on the latency and security trade-offs that an application wants to make. Okay, what's the problem with using sequencer preconfs? Can I use it safely? The elephant in the room is Ethereum finality. Ethereum finality prevents safe low latency composability across rollups. To set some context, we're going to try to understand the problem here. The canonical Ethereum chain represents this sacred timeline, if any of you watch Marvel movies, where there's many different forks sub-Ethereum finality. So anything below the 12-minute mark, you're going to see a lot of these local forks that can happen. Rollups themselves build off of different points in Ethereum history. Arbitrum may build off of depth that is deeper than that of base or that of optimism. And depending on where the rollup is building their blocks off of, their block that is created now is actually associated with a time in the past. If I'm building off a finalized Ethereum state, I'm actually building off a past state of Ethereum, or have an older block than that's being produced by base, which may be building off a newer state of Ethereum. Now, what happens when there's a reorg? If a rollup is building off a state of Ethereum that is not the one that's eventually finalized, the state of the rollup is reset. And if we think of rollup state as 2 inputs, one being a layer 1 input, deposit transactions, force included transactions, and so on, and 2 being a layer 2 input, transactions submitted to the sequencer, the layer 1 history here is the thing that's changing. The layer 2 history can be replayed, and that's okay. Now, what's the solution to this reorg problem? And how do we make sequencer preconfs go fast? We published a rollup improvement proposal, maybe not the best acronym, but it's consistent with their nomenclature. And we published this RIP around trying to specify some safety invariants and a protocol to ensure that we can communicate safely between rollups, sub-finality, and handle reorgs in protocol, which doesn't exist today. So the first safety invariant that we established is that the future cannot communicate with the past. And for anyone that watches time travel movies, you can't get on the phone and call your past self. It doesn't work. And the reason this doesn't work is because you can have a reorg where that only affects the rollup that's building off of future Ethereum state, and it doesn't touch the rollup that's building off of older Ethereum state. This means that future to past communication is a safety violation. The second invariant that we established is that you cannot communicate across different timelines. And this is also true. If you watch the alternate reality time travel movies, you'll see that if I'm in one timeline, I can't communicate with my alternate self in another timeline, unless I cross dimensions or have some sort of interdimensional transport mechanism. And the reason why we want to reject community across L1 histories is that if I'm if two rollups are on two different histories, either one rollup will reorg or the other one will. You can't have two Ethereum histories that get finalized together. The third invariant that is that once we establish a contingency link between two layer twos, that the link specifies that either both rollups will reorg together or none at all. And the fourth invariant that we established is that replaying of reorg transactions is not allowed. This means that a reorg transaction may use state that no longer exists or no longer is true post reorg. So we want to reject anything and disallow any replay attack. So Polymer goes vroom. We combine sequencer preconfs with RAP 7789, and we get a Lambo. And the last message I want to leave for the audience is that we want to embrace abundance and shun scarcity. When there's abundance, we can bring costs down. When there's scarcity, we drive users and builders away from our space. This is something that's been happening in Solana, and we can see the market and builders respond to that, as well as retail. And it's something that we will look into doing on Ethereum. And it's a path forward to bringing the world on chain. Increase bandwidth, reduce latency. If anyone's interested in building with Polymer, feel free to reach out to us on DMs. Also, please subscribe to notifications on the Polymer Twitter. We're going to be making a pretty big announcement in the coming days. Thank you.